So this is the Physics 1 Lab 1. And the basic premise of this lab is analyzing an object that is maintaining a constant velocity in a single direction using VPython and Tracker. So basically, what are the actual physical concepts and principles that are being applied here or being involved? Fnet is equal to 0 in this case because there's no change of velocity. We know F is equal to ma because of Newton's second law. Velocity is only one dimension plus x because it shouldn't move anywhere up and down in the y direction and really shouldn't move in the z, so that's negligible. Mass is not a factor because of Newton's second law. Um, Position versus time graph should constantly increase because um, of the movement of displacement due to a constant positive velocity, and that will be discussed a little bit more in detail later. So what are the parameters for the experiment? Well, for this lab, I took data from a video of a person walking at a constant velocity in their dorm. I picked this instead of the common object of rolling a ball or some other object because I think that a person walking is easier to control in terms of constant velocity. And the calibration for Tracker, which I will show now, was from the front to the back of the head. And this was about 17 centimeters or so. And I picked the center of mass around the back of the glasses. And I had the axes labeled at that first point of, or center of mass, I should say. And the time frame was about 2 seconds or so. So as we notice, it does dip a little below the axis, so he doesn't exactly stay straight up in the same y area, but that's really not a big deal because that's not really being counted. As we can see here from the graph of x, it seems to be pretty constant, so that's a good thing. Now we have the Python details for the computational model. Delta t is 0.01 seconds. And I took the first point and a second point, which was actually the third center mass I took. I took these 2 points, found the time difference, found the distance difference, distance over time, and I found the velocity, which was 0.25 meters per second. And I put this into Python because obviously you need the velocity, you need the initial point, among other things. So I guess I could show you the code. As we see here, we have the force vector, which is 0, as we talked about, because Fnet is 0. We have the change of velocity equation, change in position equation, the ball's velocity, and we have the ball's position in vector form, and the ball's mass, which is obviously not too important, of course. And let's talk about the graph a little bit. So obviously this is the graph I showed earlier, which was in Tracker. And this is the comparison between the Tracker graph and the experimental, or I'm sorry, the model, the computational model. So the red is the computational model and the blue is the Tracker graph. And so what we notice is that if we're extrapolating from those first few points and putting that into a computational model, it's actually a bit lower, or covers less area, it's lower slope than the actual on the Tracker. And so what we notice is that the person who's acting as the object in this case is speeding up a little bit. But also another idea is actually that it could be the center of mass is off a little bit on some of those points. If we look back here, if you look, not all of them are totally consistent, so that can lead to some discrepancies. So I would say overall that the lab was a relative success. I mean, Obviously, there is some discrepancy between the computational model and the experimental, but we did get nothing that was too ridiculous in terms of having a linear relationship between the position and time. So that is it.